Step 2 from 2022. This is question number 8. It's another matrices question. So M is this matrix here with A not equaling D. I don't think that's going to matter until the end of the question, really. And now M apparently has exactly two distinct invariant lines through the origin. So through the origin means that y equals mx, right? Those are lines through the origin. And if you're invariant line under a matrix, then that means that if you take A, B, C, D, the matrix itself, and you times by x, mx. Now, this is x, mx because, of course, your input is x and your output, y, is just mx. So this is the xy point where y is just mx. That doesn't need to take you to x, mx. That would be an invariant point. An invariant line needs to take you from this line to anywhere else on the line. So some other input, x prime, taking you to a different output, mx prime, but still on the line because x prime equals, because essentially the y coordinate is mx prime, right? So that's all fine. Now we can just compare this first row and the second row here. So the first row is made from ax plus bmx, and that's got to equal x prime. And the second row, likewise, has got to equal mx prime. We can replace this x prime with this here and expand out. And now, okay, one solution to this is x equals 0. But if x isn't 0, then it's necessary that c plus dm would equal am plus bm squared. Now, I'll get to this case in a second. But right now, if we continue with this, we can rearrange that and we'll end up with this here, which is what they wanted us to get. Now, what if x was 0? Now, think about what is the line x equals 0? Well, that's just the y-axis, right? So that's what they're talking about here. That's just the y-axis. And x equals 0 is just any point. It's a collection of points where x is 0 and y is whatever you want. So what we can do is we can say, okay, well, let's go from the matrix. Let's look at the matrix again and consider the line instead of y equals mx, because this is like the one line you can't write like this. So we'll consider this case first, 0y taking you to 0y prime. And again, we'll do the tops and the bottom separately, which give us this. Now, y can be whatever you want here. So therefore, b has to be 0. If we then use that and look back at a regular line, because there's got to be two distinct invariant lines, right? So we've got the first in this case where x is 0, the line y-axis. And now we'll look for the other one, because that's implied that b is 0. So now we can look for the other one with a b being 0 there, which is going to make the maths a bit easier. Again, compare the top row and the bottom row, put the x prime in there, and now x can't be 0 anymore because x has already been 0 to get your first invariant line, and the two lines are distinct apparently. So okay, now we have to have that c plus dm equals am, and when we divide, we will have our answer for m if one of the ones is the y-axis. If not, then it's just the two answers to this equation here. Good. Okay, so we've got all that down. Show that if the angle between the two invariant lines is 45. Now, the only way that I know anything about angles between lines is if I actually consider those lines to be vectors and then use the whole a dot b dot equals ab cos theta idea. So okay, the first thing, and also the other thing that we should say is, well, there's a few things we should say, but the other thing we should say is that we've got two cases, right? We've got the case that's governed by this idea where one of the lines is the y-axis and the other isn't. And then we've got the case here where neither of them are. So we're going to have to do those both separately. So the first case I'll consider is the one where neither are the y-axis, where neither are x equals 0, and then I'll do the other one. Now, okay, so how do we turn these ideas then into a vector idea so that we can use this 45 degrees? Well, if you just have a gradient m, that means you're going across 1 every time you go up n, based on the very simple definition of gradient you learned in like year 7 or 8. But that's the vector 1m, is it not? And so therefore, and the other one, of course, would have gradient n, maybe, the corresponding other one that's here. So therefore, we can say 1m, which is the vector for gradient m, dotted with 1n equals the length of the vector. Now, the length of this is 1 squared plus m squared, square rooted, times the other one, times cos 45. Cos 45 is 1 over root 2, so you can put that all underneath a single root here. This is just 1 plus mn. And then we can square both sides, maybe, and maybe even times everything by 2. Now, where is this going? And I think this is probably the hardest bit of the question, is to figure out how on earth this is helpful. And the reason that it's helpful is because if you just do some quite intelligent rearranging, I'm going to factorize for m plus n, and I also want some mn's. And I'll kind of explain why I want that. But okay, so over here, you're going to get an m squared plus n squared plus 2 mn's. Over there are 4 mn's, so I think I need 6 of those to counteract that. This, by the way, just comes from this minus this. But I need 6 of these over here because there's going to be another 2 of them over there, which will cancel down to make 4. And then, of course, 2 take away 1 is just 1. So I think this rearranges to make this. Now, why have I done that? I've done that because this equation is what's going to be useful here. Remember, m and n are the solutions to this equation. Um, m being one of them. I've probably been a bit dumb using m and n when there's just an m here, but this has two solutions, and I'm going to call them m and n, is what I'm saying. So, okay, anyway, how does that help? Well, if you've got two solutions to a quadratic equation, then by the whole roots of polynomials idea that you've done in A-level further maths, you know that the two roots sum to make this over this. No, they don't. They sum to make this over this, and it's actually minus this over this, isn't it? And they multiply to make this over this. So I can write that m times n is minus c over b. There's two of them here, so there's no extra minus to cancel anything. And m plus n is minus this one over this one. And now I can just throw those two results in. That was the reason I played around with this to create these kind of objects, because this is just mn all squared. And m plus n is just here, and m is just there. I can throw all of that business in, times everything by b squared, maybe, to get this, and then this tidies up. This sort of factorizes as long as you ignore 4 of the bc's, then it factorizes fantastically. So you just write it like this, and that's what they wanted there. So that's case number 1, where both lines were not y equals 0. So what about case 2, where 1 is x equals 0? Well, this is a slightly more difficult one. It's annoyed me so much that I was thinking, this whole time I was thinking about whether to point out, this isn't a 0, this is an O. I mean it to be a 0. I've just misclicked, and it's really annoying me. This is meant to say 0. No one would have noticed that, I'm sure, if I hadn't have just pointed it out, but it was annoying me so much. Anyway, we've done the first case. The second case is where one of them is x equals 0. Now, we saw in the previous maths that this implies that b has to be 0. That's what we learned earlier. And of course, if you've got an angle of 45 degrees between them, and one of your lines is just going straight up, that means the other one is going 45 degrees this way or this way. But of course, a line with gradient 45 degrees, or angle making 45 degrees, is just gradient 1, is it not? Because 45 degrees, you go across and up 1 and 1, so therefore it's gradient 1. Or minus 1 if it's going the other way. So, okay, well, that means we can set plus or minus 1 equal to this business here, because that was the case that dictated the other gradient if one of them was the y-axis, which is the case we're in. Times everything by a minus d. To get rid of this plus minus, we could just square both sides. And this doesn't really look like this, but b is 0, remember, in this case. So I could totally legit write that as this, because if b is 0, this just turns into minus c all squared, which is just c squared, and that's a 0. So fantastic, it's satisfied for both cases, and we're done with that. Find a necessary and sufficient condition for some of these things for the two lines to make equal angles with y equals x. Again, two cases to go through here. The case where one of the lines is y equals 0. No, x equals 0, I'm correct the first time. And the other case where they're not. So let's do the x equals 0 case first. I typed it correctly this time, fantastic. And now also, y equals x is I'm going to think of it as the vector 1, 1, right? Because it's just going 1 across, 1 up, as we just talked about with the angle 45 degree thing. Now, if one of your lines is x equals 0, it's going straight up. So if that makes an equal angle with the line y equals x to the other invariant line, that of course means the other invariant line is just y equals 0, because then it's 45 degrees, 45 degrees. So okay, the other one is y equals 0, fantastic. Now if y equals 0, that means you could, I guess, write this as y equals 0x. The gradient is 0, which means up here, because remember, this is the case where 1 is the y-axis, which is here. If m is 0, which it is here, flat gradient, then c is 0. Fantastic. And also we have that, we don't need to worry about the a equaling d business because of this up here. So we don't need to worry too much about that, so that's fine. We also get, if c is 0, we also then get from there that b must be 0. But we have that because of the previous question, or the previous bit where in this universe, b was always 0 anyway. So those are the two conditions that we'll have on the first case. The second case, and actually, maybe, so those are necessary coming from here. Are they sufficient? So if we just set b and c to be 0, and then times it by 0, 1, which is this line here, well, that, yeah, sure, that gets us here still, so that's invariant. And then if we do it with the 1, 0, it also makes something that's like this, so that's also invariant. So I think that means it's sufficient in this case, just having these two things. It doesn't matter what the other two things are. So I think I've done that for both. Now the other case is when both of them are like diagonal lines. So okay, let's set up that 1m, so this is the first gradient, if you dot that with 1, 1, which is this one here, and then do root A, root B business, that makes cos theta. So this is just the dot product definition thing here. Now, if I also have another line with gradient n, I can set up the same sort of thing here. And where does this cos minus theta come from? Well, if you've got one thing here making an angle of theta to the y equals x line, then the other one you could sort of define as making angle minus theta to the y equals x line. But cos of minus theta is the same of cos of theta because it's an even function. So therefore, we can just rearrange both of these for cos theta, because this is a cos theta, and say 1 plus m, which is what this is, over all of this stuff, is equal to 1 plus n over all of this stuff, because I've just rearranged for cos theta and set them equal to each other. And now the root 2's cancel, obviously, and you can square everything here to get rid of the square roots. And then you just, I paused here because I wasn't sure where I was going with this. I was really annoyed that this wasn't like an m squared minus 1, so that I could do some fancy cancelling. But it's not. All I thought to do eventually, after I gave up trying to find something smart, was just expand out, and then just expand out even more. So cross multiply this, expand out even more. And what happens is almost everything goes away, right? Like almost everything, except for a couple of terms on either side, just goes away. You can divide everything by 2, and you can shift some things over. And now we have this equation here. Not obvious what to do with it at all. However, what you can notice is that this is kind of symmetrical, or sort of, around m and n. More specifically, if you substituted n in for m, you would get n cubed plus n minus n cubed equals 0. So therefore, if m equals n, then you get 0. It's a solution to the equation. So therefore, m minus n is a factor of this thing here. And that leads me to think, well, this can just factorize then, right? So m has to times by 1 to get this m here, and then this would also give me the minus n from there. And then how do I get like this mn squared? It's tempting to think, well, I need to do m times, mn, I guess, or I need to do n times mn. Either one is fine. It just works. I think it just about works. You can verify it and you can sort of expand it out, but it does just work quite nicely. So that's all good. Yeah, quite a nice little use of factor theorem there. Something that STEP uses a few times. So try spotting symmetries if you've got a couple of letters and something like this, because factor theorem might help you out if you do that. Of course, this implies that either m equals n, which it can't, because that means the two lines have the same gradient and they're supposed to be distinct. So therefore, instead, mn must equal 1, which means m is 1 over n, which I'm actually not going to use, because now we can go back to this idea up here, where in this case, where we're not considering a vertical line, they satisfy this equation. The m and the n, they satisfy this equation, don't they? Which means when you multiply them together, again, it's just this one over this one. No, it's not. Yes, it is. It's this one over this one. So therefore, 1 is minus c over b, as we saw before. And we can just write this as b plus c equals 0, which is interesting that this is essentially going back to the first case where b and c were both 0. I guess this satisfies b plus c equals 0 as well. So it's just a more strict case of that. I'm not really sure. Something else I'm not too sure about is the sufficiency case here. I racked my brains for a long time thinking about how to check this is sufficient. And aside from just sort of hand-wavy claiming that all of these steps are reversible, which I'm pretty sure they are because it's just algebra. I mean, that's what I would write in the exam. I would just say all the steps are reversible, so it's sufficient, mate, move on. I wasn't sure how to do it otherwise. And the mark scheme, unfortunately, wasn't very helpful because it didn't seem to do it either. So maybe I'm right when I just say that the steps are reversible and we can just say that. If you can't, and if you know what to do here, please let us know in the comments. That would be really helpful. Anyway, our last part of this question is nice and simple, actually. Give an example of a matrix that satisfies both 2 and 3. So okay, well, we just have a 2 by 2 matrix. It's got to have b plus c equals 0, because that was the thing that we just saw, which means b is minus c. So let's just throw in maybe 1 and minus 1. That'll do. And it's also got to do this. So let's now put in b is minus 1, or b is 1 and c is minus 1, and we get this, because that makes a plus 1. No, it doesn't. Yeah, no, that makes a minus 1, which makes this a plus 4. And that's a 1 minus 1, which is a 2. That makes 8 rooted as 2 root 2, or plus minus 2 root 2, I should say. So I just need an a and a d that take away to make 2 root 2 or minus root 2, 2 root 2. It doesn't matter which I do. I went for root 2 and minus root 2, which I think will work. And I think that will be the whole question done. Thanks for watching.